On the north shore of Oahu, in the midst of this miracle mile, sits the famous wave pipeline. It's here where the world's best surfers come to prove their skill. And while they sit out in the water and wait for that next set of waves to come, it can get kind of crowded out there. But when those waves come and that one surfer decides to drop in, it's look out below, and the other ones better get out of the way. Now this situation actually reminds me of the colligative properties of solutions, and these are properties that solutions have that pure solvents do not, and the reason is simply this: the solute particles get in the way. So while you prepare for this next lecture, take a look at some of these infamous waves at pipeline. Aloha and welcome back. This lecture is the last one we'll do on solutions, and today we focus on the colligative properties. These are properties of solutions that depend on the number of dissolved particles and not their type. So solutions have special properties that pure solvents do not, and further, these properties only depend on how many dissolved particles there are. It doesn't matter if those particles are sugar particles or if they are some other particle like salt or CO2 or whatever. It just depends on how many particles are in the solution. So, the properties of solutions are different than properties of pure solvents. Now that's interesting. Solutions have these properties, but pure solvents do not. Why is that? Well, the reason is actually fairly simple. The solute particles just get in the way. Now, as we discuss these four colligative properties, try and see if you can predict how these solute particles get in the way. The first colligative property is vapor pressure lowering. Solutions have a lower vapor pressure than pure solvents. I'll remind you that we discussed vapor pressure in lecture 4, and we'll just recall that very briefly right here. Suppose you have a container with pure water and you cork the top of that container. The water will vaporize some of it. Those more energetic particles will vaporize, and once the vapor is up here, those particles will collide with the walls of the container and maybe lose a little bit of kinetic energy, and some of those less energetic particles will get trapped again by the solvent. And so you have water vaporizing and you will have water condensing, and once the system settles down, the rate at which those two processes occur are equal and pointing in opposite directions. And so the chemical equation can be represented like this. Now, the pressure of the gaseous water particles up here is called the vapor pressure. And at about 25 degrees Celsius, it's about 24 torr. Now, the rate of vaporization actually depends on a couple of factors. It depends on the temperature. So the vapor pressure depends on temperature, but more specifically, the rate of vaporization depends on this. And also, it depends on the surface area. Now, the vaporization is only occurring at the surface here. Think of what happens if we introduce a solute, say sucrose or table sugar. So if you open up the cork and you put some sucrose in there, then that sucrose will end up being dissolved in the liquid. And if you put quite a lot of sucrose in there, then you'll have a lot of it dissolved up here in the bulk phase and also on the surface. And since it's distributed along the surface, it's actually blocking some of the surface. And whereas water would normally have access to those areas, it no longer has access to those areas on the surface. And so the rate of vaporization is now less than what it was before. And when you let this system settle down, the rate of vaporization will equal the rate of condensation, and you'll have a less amount of vapor up here. So the vapor pressure would be quite a bit lower. Depending on how much solute you have dissolved, you might see the vapor pressure decrease to only 12 torr. That's if 1/2 of the surface is exposed. So if the solute particles are blocking 1/2 of the surface, then the other half, water can freely vaporize, and so you'll only get 1/2 of the vapor pressure. And that's how it works. Now this little relationship can be described by Raoult's law. Raoult's law tells us that the vapor pressure above a solution equals the mole fraction of the pure solvent times the vapor pressure of the pure solvent. So if the mole fraction of water is 0.5 or 1/2, that represents 1/2 of the surface being available for water to vaporize. So you'll get 1/2 times the normal vapor pressure of water. And if the mole fraction is 3/4, so 75% of the particles are water, then you would have 3/4 times the normal vapor pressure, and so on. So for instance, suppose you wanted to find the vapor pressure of water above a solution of 1 mole glucose dissolved in 9 moles water at 25 degrees Celsius. So the vapor pressure of water above the solution would be the mole fraction of water times the pure vapor pressure of water. And the mole fraction of water is 9 moles of water divided by the total moles, which is 10. So you have 9/10 for the mole fraction. And you multiply that times the vapor pressure of water at that temperature, which is 23.9 torr. So 9/10 times 23.9 torr, you end up with 21.5 torr. So it has decreased a little bit. You still have most of the vapor pressure because most of the particles are water. Now, we can also describe the vapor pressure depending on the concentration by this graph right here. This is a graphical representation of Raoult's law. And on the y-axis is plotted the vapor pressure of water at 25 degrees Celsius, and the x-axis is the mole fraction of water. So for instance, at a mole fraction of 1, meaning it's pure water, the vapor pressure would be 23.9 torr, so that's this blue line. But at a mole fraction of 0.5, then the vapor pressure, you go up to this solid pink line, would only be about 13, 12 maybe. So you can use this graph to predict the vapor pressure of water above a solution. And again, if the mole fraction is maybe 0.75, then you would go here to 0.75 and go up here, and it's about maybe 19 or so. So it's less accurate to use the graph, probably better to use the equation. But it still gives you a nice visual representation. You see the line is a straight line, and when the mole fraction decreases down to 0, the vapor pressure also decreases down to 0. Now, what are these dashed lines above and below the solid pink line? Well, those are deviations from Raoult's law depending on the strength of the interaction between solute and solvent. Suppose the solute particles have very strong interactions with the solvent particles. They would prevent the solvent from vaporizing. So if the interactions between solute and solvent are strong, the solvent will not want to vaporize. And the vapor pressure would be less than what Raoult's law predicts. And the opposite occurs if there are weak interactions between solute and solvent. Then the solvent would more readily vaporize, because whereas water is normally interacting with other water particles, if you substitute those water particles with solute particles where the interactions between the solute and water are very weak, then water will vaporize more than what's predicted. And so this is the case for weak solute-solvent interactions. In our previous example of sugar and water, the sucrose was non-volatile, meaning it did not vaporize to any significant extent. However, sometimes the solute is volatile, and so we need to account for those situations. If the solute has a significant vapor pressure, then it must also be accounted for. For example, find the total vapor pressure over a solution that contains 1 mole water and 1 mole ethanol, which is alcohol. The pure vapor pressure for water is 23.9 torr, and that of alcohol 44.6 torr. Now we can imagine what this solution looks like by this diagram right here. The water and the alcohol completely mix. They are totally miscible. So all of the molecules will be intermingled, and likewise at the surface you will have water and alcohol molecules. Now the water wants to vaporize with its own vapor pressure. However, the alcohol, at least some of it, is in the way. And likewise with the alcohol, it wants to vaporize, but the water is in the way. Now, to find the total vapor pressure above the solution, we need to add the vapor pressure of water, which will be less than what it normally is, along with the vapor pressure of alcohol, which will be less than what it normally is. So the total vapor pressure will be the pressure due to water. This is applying Raoult's law for water, plus the vapor pressure of the alcohol, Raoult's law for alcohol. Now the mole fraction for water is 1/2. So 1/2 times the pure vapor pressure of water, 1/2 times the vapor pressure of alcohol. And adding these two components, we get 34.25 torr. Now this is the total pressure above the solution. This pressure here is actually halfway between the two individual pressures. And that's because we have a mole fraction of 1/2. We can better understand this perhaps by looking at the following graph, which plots vapor pressure on the y-axis versus mole fraction of water on the x. Now, I've drawn two y-axes here for convenience. If the mole fraction of water is 1, then the pressure over the liquid, which is pure water in this case, will be 23.9 torr. And if the mole fraction of water is 0, then we have pure alcohol, and the vapor pressure of the pure alcohol is 44.6 torr. Now, by connecting these 2 points with a straight line, that's actually accounting for any mole fraction that we can consider. If the mole fraction is 1/2, like in our example, then we go up to the line and we go over, and we see that we get 34.3 torr. And this is actually halfway between the two vapor pressures. And we can consider any mole fraction. Suppose the mole fraction of water is 9/10 or 0.9. We go up to the line and we go over, and we're pretty close to water. If the mole fraction of water is 1/10, then we go up to the line and we're really close to that of alcohol. So any mole fraction can be obtained here. Kind of a cool plot. Now this is the case for any two liquid solutions where both the liquids vaporize. Suppose we have component A, which has its vapor pressure, and component B with its vapor pressure. Plotting mole fraction of B here, when the mole fraction is 1, that means we have pure B. And then this is our vapor pressure, and if it's 0, that's our vapor pressure, which is the same as A. And if we connect this line, then we get the vapor pressure of any mole fraction that we want. Now suppose the two components have strong interactions, then that will hinder the vaporization of the two components, and the vapor pressure will be less than expected. So if the interactions between A and B are strong, then the vapor pressure will be less than what we expect. We get this deviation from what Raoult's law tells us. Raoult's law tells us to look along the straight line. But if there are interactions, then we can deviate this way. And likewise, in the opposite case, if there are weak interactions between the two components, then it will be easier for them to vaporize, and we'll have a positive deviation. Now we can see what the effect of adding a solute is on the vapor pressure by looking at the phase diagram. Let's look at the phase diagram for water here and see how the solute affects it. I'll remind you, we discussed phase diagrams in lecture 5. Now, pure water has a phase diagram given by the green lines here. This is the triple point, and we have our solid, liquid, and gas phases. Now, the vapor pressure curve is the line going up this way, and this represents the pressure where the liquid and gas are in equilibrium with each other. So at this temperature, water has a vapor pressure right here. At another temperature, water has a vapor pressure right here. Now adding a solute to the mixture lowers the vapor pressure, and it does that at every single temperature. So at every single temperature, the vapor pressure becomes lower, and so the net effect is to lower the entire vapor pressure curve. Now interestingly, that's not the only part of the phase diagram affected. The solid-liquid equilibrium line is also moved to the left. And if you study this and you think about it, you might wonder if this changes the melting point. Well, you're correct. It does change the melting point. In fact, it lowers it. Because the temperature at which solid is in equilibrium with liquid, by adding a solute, that temperature becomes lower. So the melting point also decreases. The second colligative property is boiling point elevation. If you understood why the vapor pressure of a solution is lower than that of a pure solvent, then it's easy to see why its boiling point is also higher. Let's first recall what the boiling point is, and it's the temperature at which the vapor pressure is equal to the atmospheric pressure. So if you imagine a container that has some liquid in there, that liquid has a certain vapor pressure. Some of those particles at the surface are vaporizing with a certain pressure. Now meanwhile, the atmosphere is pressing down on the surface of the liquid, and if we increased the vapor pressure of the liquid by heating the liquid up, then eventually, if we heat it up enough, its vapor pressure will match the atmospheric pressure. And when that occurs, it's not just the surface particles which vaporize, but particles all throughout the liquid will start vaporizing as well. And that's why you see bubbles start to form throughout the bulk liquid, because that's vaporization occurring everywhere, and that's boiling. Now, when a solute is added to the liquid, that's going to affect the vapor pressure and also affect the boiling temperature. And we can see how by looking at this diagram right here. We have pure water on the left and a solution on the right. The solution will always have a lower vapor pressure than the pure solvent. Meanwhile, the atmosphere is always pressing down with a pressure of about 1 atmosphere. If we wanted to boil these two liquids, we'd have to heat them up in order for their vapor pressures to reach 1 atmosphere. Well, we know that the pure water will have to be heated up to 100 degrees Celsius, and when it reaches 100 degrees Celsius, its vapor pressure is 1 atmosphere, and that's why it starts boiling at that temperature, because that vapor pressure is matching 1 atmosphere, which is the atmospheric pressure. But the solution will have a lower vapor pressure than that, and it won't be boiling yet. Its vapor pressure will still be smaller than 1 atmosphere. To make it reach 1 atmosphere, we have to heat this one up a little bit higher. And that's why the boiling point is higher for a solution. Now we can see this effect on the phase diagram of a substance as well. If we look at the phase diagram for substance, any substance, it shows us the different phases of the substance. And over here you have your vapor pressure curve. These blue lines right here represent the pure substance. And so for a pure liquid, in order for its vapor pressure to equal 1 atmosphere, which is represented by this horizontal line, it will have to be brought to this temperature right here. When there's a solution, the solution will always have a lower vapor pressure, which is represented by the pink lines right here. And so in order for the solution to be brought up to 1 atmosphere of vapor pressure, it needs to be raised to this temperature. So you see the boiling point has increased a little bit, as indicated by the phase diagram. Now, how much does it increase? It's a pretty simple relation. The change in the boiling temperature is equal to the molality concentration times a constant, which is called the boiling point elevation constant. And these constants are different for every liquid, every solvent. And I've listed several solvents here along with their constants. Here is some freezing point data that we'll get to in just a moment, but over on the right is boiling data. And there are several boiling temperatures of the pure solvents along with their boiling point elevation constants. So water boils at exactly 100 degrees Celsius, and if you look at some of the other liquids, it's interesting that the ether boils at 35 degrees Celsius, close to it. In fact, that's around 95 degrees Fahrenheit. In fact, if you hold a container of ether, you might be able to boil it just with your hands. So kind of interesting. Water has a boiling point elevation constant of 0.512 degrees Celsius per molality. So every single molality will raise the boiling point by 0.512 degrees. If the solution has 1 molality of particles, the boiling point increases by 0.512 degrees. And if there are 2 molality of particles, its boiling temperature increases by twice that much. 3 molality of particles, it increases by 3 times this much. It's this many degrees per molality. So you have to multiply the number of molality of particles times the boiling point elevation constant. So for instance, suppose you wanted to find the boiling point of 1.7 molality aqueous sucrose solution. So this aqueous means that water is the solvent. So we find the boiling point elevation constant for water, and we multiply that by the concentration, and we get 0.8704 degrees Celsius, which rounds to 0.87. And so that's how much it increases. So we have to add that to the original boiling temperature, and the new boiling temperature is 100.87 degrees Celsius. So the solution has a slightly higher boiling temperature than pure water. Now the freezing point is also affected by the presence of a solute, and we can see how that works by this diagram. This is the third colligative property, the freezing point depression. It gets lower. So here's a solution of some solute dissolved in water, and this solution is being cooled down cold enough to start to form ice. It's interesting that this ice that's forming amidst the solution is pure water. So there are no solute particles trapped in the ice, or relatively few. So pure water is what freezes out of the solution. Now the reason it does this is because of those strong hydrogen bond interactions between the water molecules, which help pull them together to form the ice. That's not really important for this discussion right here, but that's why it does it. And since the pure water is what freezes out of the solution, these solute particles that are surrounding that ice are getting in the way. As this ice cube begins to grow, more and more water molecules need to find their way to the ice cube to make it get bigger. Well, if the solute particles are getting in the way, it's going to make it hard for a water molecule to find its way to the ice. In fact, at hotter temperatures, that tends to stir up everything and make it more difficult for water to find its way to the ice. It would make it more difficult for the freezing to occur. And so the solution would have to be cooled down that much more to allow the water to form the ice. And that's why the freezing point is lower for a solution than pure water. And we can also see this effect on the phase diagram. Here's that same phase diagram. And you can see the solution is represented by the pink curve. And over here, this is your freezing curve. Now the blue line is the pure substance. And in order to melt or to freeze, it would have to be at this temperature right here. But for the solution, that shifts this freezing curve to the left, and the freezing temperature is a little bit colder for the solution. How much does it change the freezing point by? Well, that's also given by a similar equation as we saw before. The change in the freezing temperature is equal to the molality concentration times the freezing point depression constant. Now, rather than jump right into an example, I wanted to first quickly discuss the case for solutions of ionic compounds. Because when you have an ionic compound, that adds a little bit of complication to the mix. For instance, when you take 1 mole of sodium chloride and you dissolve it in water, we know that ionic compounds dissociate into their cations and anions. So 1 mole of sodium chloride will give you 2 moles of particles. In other words, you'll have twice as many particles as what you might expect. And that means you'll have double the effect on the colligative property. Because remember, colligative properties, it doesn't matter what type of particle it is, it just depends on how many there are. So when you dissolve 1 mole of sodium chloride, you're going to get twice as many particles. Now there's one little catch, and that catch is it seems like you would get twice as many particles, but in reality, you'd only have 1.9 times as many. Now the reason that it's not 2 times as many particles is because If you imagine a container where you dissolve 1 mole of sodium chloride in water, and all of those cations become separated from the anions. So you have all of your cations and anions floating around independently of one another. It seems like you have 2 moles of particles, and that would be a correct assumption. However, if you look carefully, sometimes every once in a while you'll see a cation right next to an anion. So it just happens, every once in a while, but a small fraction of those ions will be kind of close together, and that's kind of like 1 particle. And so instead of there being 2 moles of ions, you'll have a little bit less than 2. It's closer to 1.9. And this number over here is called the Van't Hoff factor for sodium chloride. And all ionic compounds have their own Van't Hoff factors. For instance, magnesium chloride should dissociate into 3 ions, your magnesium 2+ and your 2 chloride ions. However, the Van't Hoff factor shows that it's actually closer to 2.7. Iron 3 chloride should give you 4 particles, your iron 3+ and your 3 chlorides, but the Van't Hoff factor is actually 3.4. Now these Van't Hoff factors are determined experimentally by measuring what the colligative property is and going back and comparing it with what you'd expect, and you're able to work out, how many particles are actually in the solution. For instance, if you measure the change in the boiling temperature and the constant for the solvent, then you should be able to determine the molality of the particles. And that's how you find these Van't Hoff factors. So whatever the molality of the particles is, or whatever the molality of the solute is, you'd have to multiply it by its Van't Hoff factor. So this equation for the freezing point depression is modified a little bit to account for the dissociation of ionic compounds. So you multiply the molality times the Van't Hoff factor, and then you multiply it by the freezing point depression constant. And that's how it's accounted for this colligative property. In the other colligative properties, you have to account for ionic compounds as well, but we'll just do it for this one case, for the freezing point. So for instance, find the melting point of 0.9 molality iron 3 chloride aqueous solution. So the molality is 0.9, but it's iron 3 chloride. So we have the ionic compound dissociating not into 4 particles like we might expect, but it's actually closer to 3.4. So when we multiply the Van't Hoff factor times the molality concentration times the freezing point depression constant, you can go back for water, and now you can find its freezing point depression constant is 1.86 degrees Celsius per molality. When you multiply these out, you get 5.6916 degrees Celsius, which will round to 6 degrees. So the freezing point gets lower by 6 degrees Celsius. So you subtract this many degrees from the original freezing point for water, and so the new freezing point is -6 degrees Celsius. The fourth and final colligative property is osmotic pressure. To see what osmotic pressure is and how it works, let's look at the following diagram. Here we have a U-shaped device in which we pour pure water on the left and some type of solution on the right. Now, separating these two liquids is some membrane, and we call that a semi-permeable membrane. And that's because it only allows the solvent to pass through the membrane. So water is allowed to pass through, but the solute particles are not. So it stops the solute particles from passing through. Now, if we set this device up like that, at the very beginning, these liquid levels are even. But what we'll see if we wait a little while is that water will end up flowing in this direction through the membrane, and these liquid levels will end up changing, and the liquid level on the solution side will end up being higher than the pure solvent side. Well, that's kind of interesting, because if water is able to freely travel through this membrane, why does the water end up doing that? Why wouldn't it just flow back the other direction? What's holding it up there? Well, what's holding it up there is the osmotic pressure that's exhibited by the solute particles in solution. You see, a solution tries to expand its volume by incorporating more solvent. And what's doing that are the solute particles. So these solute particles are sort of moving around in this solution, and they're exerting a pressure. And that's what's making the solution expand its volume, and that's what's holding up that extra weight of water. But let's first take a closer look at what's going on the molecular level, and let's take a closer look at the semi-permeable membrane. You see, this semi-permeable membrane only allows the solvent to pass through. And if you think about the situation right at the beginning, when you pour the two liquids in there and the two liquid levels are the same, let's look at this membrane, and on the left-hand side of the membrane you'll see solvent particles only. And these solvent particles, a certain fraction of them will be traveling that way, and then a certain fraction will be traveling this way through the membrane. Now, on this side of the membrane, you will have not only solvent particles, but also some solute particles. And those solute particles are blocking up some of the membrane. So they're occupying some of those sites next to the membrane, and so you're not going to have as much water traveling the other direction. So on the left-hand side, there will be a lot of water traveling this way, but on the right-hand side, only a little bit of water traveling the opposite direction. And that's just based on the random motion of the particles next to the membrane. So what happens is that water ends up moving this direction through the membrane, and it's going to keep on doing that until finally there's so much weight of water up there that the weight sort of balances that tendency for it to travel in this direction. So this weight of water up here is held in place by the osmotic pressure of the solution. So it's these solute particles that are sort of moving around and creating a pressure inside there. So the way you'd calculate this pressure is kind of simple. The pressure, which is represented by the Greek letter pi, is equal to the molarity concentration times the gas constant R times the temperature. Now, if you recall from first semester general chemistry, this equation might look kind of familiar. And that's because if you recall the ideal gas law, PV equals nRT, that's the pressure of a gas times its volume, is equal to the number of moles times the gas constant times the temperature. And if we rearrange this equation and solve for the pressure, we get the pressure is equal to N over V, RT, but N over V is the same thing as the molarity. And so the pressure of an ideal gas is equal to the molarity times R times T, and that is the same as the pressure exerted by the solute particles inside of a solution. So it's very interesting how the pressure of a solution is calculated using the same equation as the pressure of an ideal gas. And it's not really a coincidence either. What it's telling us is that solute particles behave very similarly to gas particles. In fact, it has been shown that solute particles move around with similar velocities inside of a solution as gas particles do in the air. And so the pressure exerted by solute particles on the walls of their container would be similar to the pressure exerted by the gas particles on the walls of their container. And that's why these equations are very similar. In fact, they're basically equivalent. Now, solute particles move around and exert pressure just like gas particles do. So that's the take-home message here. So we can calculate osmotic pressure fairly easily if you know the molarity and you know the temperature of the solution. Then you can just plug it in and calculate it. But let's do a rather more interesting calculation involving osmotic pressure. Here's our example. A solution containing 35.0 grams of the protein hemoglobin dissolved in water to form 1 liter of solution. Now this exerts an osmotic pressure of 10 torr at 25 degrees Celsius. Find the molar mass of hemoglobin. So here you're given the temperature and you're given the pressure. So you have the temperature, you have the pressure, and we always know what the gas constant is. So we can calculate the molarity of this solution, right? It's not asking for the molarity though, it's asking for the molar mass. But what you should remember is that the molarity, which is equal to the number of moles over the volume, can be expressed in a different way. You see, the number of moles is also equal to the mass divided by the molar mass. And so if we replace the number of moles by mass over molar mass, and then all of that over the volume, that's also equal to the molarity. And this simplifies to that. The molar mass comes down. And so the molarity is equal to the mass over the molar mass and the volume. And so if you take this expression for the molarity and you plug it in for the osmotic pressure, you see the osmotic pressure equals m over the molar mass and the volume times r times t. And here, if you look at this expression right here for the osmotic pressure, we know what everything is except for the molar mass. And if we rearrange this equation and solve for the molar mass, we can then calculate it pretty easily because we know all of the variables over here on the right. So doing that, now we have to be careful of our units too. So let's be careful of our units and let's see how it goes. The molar mass is equal to the mass, 35 grams, times the gas constant, 0.08206 liter atmosphere per Kelvin mole, and then times the Kelvin temperature. So 25 degrees Celsius is 298 Kelvin. In the denominator, we have pressure and volume, but we want the pressure in atmosphere. So we take our 10 torr and we convert it to atmosphere. And then we also put the volume down there, 1 liter. And a lot of units cancel off. You can see how they cancel off. And what you'll end up with are grams per mole. And you end up with 65,047 grams per mole, which rounds to 6.50 times 10 to the fourth, or just 65,000 grams per mole. That's a pretty large molar mass, but again, we're talking about a very large protein molecule. There are several applications of osmotic pressure, and we don't have time to go through all of them, but I tried to choose a few interesting ones. The first one is a common application which involves medical solutions. And nurses out there who have to make up IVs and inject them into the body, well, they have to be careful and inject the right type of solution. If you inject too salty of a solution, with too much saline or too little, that can adversely affect the patient. And you can imagine cells in the body, in the bloodstream, they have solute particles inside the cell, and there are also solute particles outside the cell. And if the concentration of solute outside is similar to what's inside, then there is no osmotic pressure involved here. And so the cell will maintain its size. But suppose a nurse were to inject a very salty or saline solution, and the concentration of solute is more outside the cell. Well, this cell membrane can act as a semi-permeable membrane. And what happens, again, solvent will always try to travel to the solution. And so the cytosol fluid inside this cell will end up trying to escape out the membrane and go into the extracellular fluid. And so the cell will end up shriveling up. So you don't want that to happen. That's called a hypertonic solution. A hypotonic solution is actually opposite, where a nurse might inject a very dilute IV fluid, and in that case, that can cause the extracellular fluid to be more dilute relative to the inside of the cell. And so in that case, solvent will end up incorporating into the cell, and the cell will end up getting bigger because more solvent is traveling in through the membrane. And that can cause cells to increase in size, even rupture. So we don't want to have a hypotonic solution either. You'd probably rather have an isotonic solution, right? That doesn't disturb the cells. Application 2, osmotic pressure is also the mechanism by which water moves up a tree trunk. And here in Hawaii, we have our nice, beautiful palm trees. Some of them are pretty tall. And what happens is that these leaves on top of the tree, water vapor ends up escaping the leaves and into the vapor phase. And that leaves concentrated leaf fluids inside the leaf cells. And when there are concentrated fluids in those leaf cells, the pure solvent or water, which is in the ground, will end up traveling up through the trunk to try to get into the concentrated region. Remember, pure water, again, always travels towards more concentrated regions because of osmotic pressure pulling it. And so the osmotic pressure will pull the water up through the trunk. In fact, palm trees may be 50 feet high, but some big trees, like in the redwood forest of Northern California, which can get up to 100-200 feet, it has been estimated that an osmotic pressure up to 10 to 15 atmospheres is responsible for pulling that water up those big trees. So, quite something. Now, the last application is making a pickle. You can imagine taking a cucumber. The cucumber has a nice skin coating which can act as a semi-permeable membrane. And if you surround the cucumber by some salty solution, then the water inside the cucumber will want to travel through the membrane to the salty area outside, and so the cucumber will end up shriveling up, and that's how you make a pickle. I hope you have enjoyed this lecture on the colligative properties. This does close up our second portion of the course on solutions. In the next portion, we move toward the chemical reaction rate, which deals with how fast a chemical reaction goes. So we're getting ready to switch gears here. Stay tuned, and aloha.